Next topic is a general characteristic of open channel flow. Open channel flow is classified based on the water depth y, vary with time t, and vary with distance x. Okay. The first group we call the unsteady and steady flow, depending on whether the depth at a given location does or does not change with time. Okay. In case of change with time, we call the unsteady. In case of doesn't change with time, we call the steady flow. Okay. For the uniform flow, if the depth of flow does not vary along with the channel, so dy over dx is equal to 0. For non-uniform flow or vary flow, if the depth is vary with the distance, or dy over dx is not equal to 0. Non-uniform flow can classify into groups. The first is we call rapidly vary flow, and so dy over dx is equal to 1, and the second is gradually vary flow, dy over dx is less than 1. Okay, and this show the uniform flow. This figure for uniform flow is mean it doesn't change with the distance. You can see the y1 and y2 are equal, and dy equal to 0. Okay, and on the right hand side is non-uniform flow, so it means the depth is changed with the distance. y1, y2 is different, so dy over dx is greater than 0. And if the change of the y is in between 0 and 1, we call the gradually vary flow, but it's about 1, we call the rapidly vary flow. And the other parameter for open channel flow may be laminar flow or turbulent flow, or in between, is depending on the real number that we learned from the flow in pi. And this show figure what is the difference between uniform flow, okay, and rapidly vary flow at the bottom of the water cat, and this hydraulic jump, and rapidly vary flow, and this is rapidly vary flow. That measures parameter that describe how fast of the water flow relative to how fast our typical wave equal the foot number, okay, is equal to v divided by square root gl. Okay, L is the characteristic length of the flow. If foot number is equal to 1, is we call the critical flow. Less than 1 is supercritical, subcritical flow, and greater than 1 is a supercritical flow. Okay. Next topic, the energy consideration. This figure shows the typical segment of open channel flow. Okay. S0 is the slope of the channel bottom is equal to the different elevation Z1, Z2, okay, Z1, Z2 divided by length L, length between the two sections. And for Z0 is very small for the natural river. For example, in Mississippi River, the drop of the distance is about 450 meters from the length about 3,780 kilometers. Okay. If the slope is 1.2 10 minus 4, 10 power minus 4. y1 and y2, if it's a depth of water, this is y1, and y2 is depth of flow at the section 1 and 2. And it's a vertical, we use the vertical depth due to the channel slope is very small, so the depth can be measured perpendicular to the channel bottom. And v1 and v2 is the velocity at the point 1 and point 2. And we can write the energy equation, Bernoulli equation between section 1 and 2 based on this equation. Okay. For this right hand side, HL is the head loss from the viscous effect between two sections. And for pressure head, P1 over gamma, we can substitute by Y1, and P2 gamma Y2. Okay. and so we can and for the difference between Z1 and Z2 we can substitute with the S0, so we got this one is the Y1 and Y2 here and S0 here, and write the head loss in form of the slope of the energy gate line, S slope SF equal to head loss divided by the length. Okay, so we got this equation. And for this equation 3, if we arrange this equation to make the y1 plus v1 square over 2g, and the right hand side for y2 v2 square over 2g, for this term we call the specific energy. Okay, we're going to go to the next section.